So what is integration? Well, integration is often called the inverse process to differentiation. What does this mean? Well, say we had a function y equals a third x cubed. Say we were to differentiate this. Well, hopefully you can work out that the derivative of this is just x squared. And to work this out, you'd probably in your head multiply down by the power. So you do the 3 times the third, which gives you 1, and then you reduce the power by 1. So 3 minus 1 gives you the 2. So that's the normal process we think about when we differentiate. Now what if we were to reverse this process? Say we started off knowing that the derivative of some function was x squared. What would we do to get back to the original function? Well, it would make sense to do the inverse of what we've just done to differentiate. So instead of multiplying down by the power, then reducing the power by 1, how about instead if we do the reverse? So we increase the power by 1, and then we divide by our new power. So how about we apply this to x squared? Well, if we do that, so we increase the power by 1, which would give us x cubed, and we divide by our new power, which is a 3, so we divide by 3, which gives us a third x cubed. Sure enough, we get back to where we started. However, there's one final step we need to add here. We need to add that we plus c at the end. We'll talk about why we plus our c in a moment. But for now, we've successfully integrated x squared. So while we say that the differential of a third x cubed is x squared, we can now say the integral of x squared is a third x cubed plus c. And to integrate this term, we've increased the power by 1, divided by the new power, so the inverse of what we would do if we were differentiating, and then we plus c at the end. Let's now look at why we add the c at the end. Let's again consider the function y equals a third x cubed. As before, we said this differentiates to x squared. Now let's consider the function y equals a third x cubed plus 4. Let's see what this differentiates to. Well, as before, the third x cubed term differentiates to x squared, and we have a constant here at the end, and constants when differentiating disappear. So once again, we're left with the differential being x squared. How about the function y equals a third x cubed minus 1? Well, if we differentiate this, once again we see that a third x cubed term differentiates to x squared, minus 1 disappears as a constant, and so once again we have the differential being x squared. What you notice here is that all these different functions differentiate to the same function. And in fact, if we added or subtracted any constant to the third x cubed, so a third x cubed plus 5, plus 100, minus 3, whatever constant term, it's always going to disappear on differentiation. So we're left with a lot of functions that differentiate to the same thing. So now if we were asked what is the integral of x squared, hopefully you can see that the answer would be a third x cubed plus c. By putting plus c, we're saying that there could have been a constant added to the end of our original function, but we're not sure which one. So by putting plus c, we account for all possible cases. The plus c is known as the constant of integration. Let's now look at some of the notation used in integral questions. Say as before, we're asked to find the integral of x squared. In mathematical notation, that can be written like this. So we have an integral sign, which looks a bit like an elongated s. Next to that we have a function, so in this case x squared, and at the end we write dx, which basically just means with respect to x. So that tells us that we're integrating x squared with respect to x. This is just like if you were differentiating, you would write dy by dx. And here again, dx is standing for with respect to x. So it's just like with differentiation, except that we put the dx next to the function instead. And of course, we'd answer this question by writing what we've just worked out as a third x cubed, and of course, plussing c at the end. It's also good to know that there are two different types of integrals. There are indefinite integrals and definite integrals. Indefinite integrals look like the example we just did. So they have the integral sign, a function, say x squared, and then dx after it. Definite integrals look very similar as well. They also have the integral sign, a function, and then dx. But the difference with definite integrals is there is also a number at the bottom and the top of the integral sign. For instance, you might have 2 on the bottom and 4 on the top. These are called the limits of integration. The way you work out indefinite integrals and definite integrals is quite similar, but we're going to talk about definite integrals in a later video, and for now, focus on indefinite integrals. Now we have our notation sorted, let's look at another example. Let's try integrate the function x cubed dx. Well, if you remember what we did before, we can do the inverse process of differentiation. So we can add 1 to the power and then divide down by the new power. So x cubed would become, well, 3 plus 1 is 4, so you add 1 to the power, and then you divide down by the 4, giving you a quarter x to the 4. And of course we then add plus c at the end to say that there could also be a constant added at the end, but we're not sure which one. Let's now think about a more formal way to talk about this process of adding 1 to the power and dividing down by the new power. If you have a look at this power rule here, it says that if we're integrating a function of the form x to the power of n, then the integral is x to the power of n plus 1 divided by n plus 1 plus c. So you can see that this is exactly the same as the process we've just been doing of adding 1 to the power and then dividing down by the new power. However, we need to be careful because there are some conditions on what the number n can be. So it says here n has to be a real number. So real numbers are most types of numbers you'll come across, so they include the integers, so that's positive numbers, negative numbers. It also includes fractions, rational numbers. It also includes irrational numbers. So there are lots of possible values for n. However, it says that n cannot be minus 1. This is really important, and we'll see what happens when n is minus 1 in a later video. But for now, know that the integral of x to the power of n we can write as this, but you need to check first that n is not minus 1. Let's try 2 more examples now using this rule. This is a good time to pause the video if you want to try these yourself first, or you can watch me go through them. So the first one here, x to the power of 7, well, we can use our power rule. We have n equals 7. 7 is not minus 1, so we can use this rule. So this tells us our answer is going to be x to the power of 7 plus 1, which is 8, divided by 7 plus 1, our new power, 8. And then we plus c at the end. So we have 1/8 x to the 8 plus c. Let's try the final one here. So initially it might not look like this x is raised to any power. However, if you remember that x is the same as x to the power of 1, so you can pretend there's a 1 here if you like, then we can use the power rule with n equals 1. So the answer is going to be x to the power of 1 plus 1, which is 2, divided by this new power, 1 plus 1 is 2, plus c. Let's see what happens with negative powers. Let's say we want to find the integral of x to the negative 2. Well, minus 2 is a real number and it's not negative 1, so we can use the power rule again. So by the power rule, the integral of x to the power of minus 2 is going to be x to the power of minus 2 plus 1, which gives us minus 1, divided by minus 2 plus 1, so that's minus 1. So again, we're just adding 1 to the power and dividing down by the new power, plus c. But we can simplify this a little, because dividing by minus 1 is the same as taking the positive sign and flipping it to negative. So we can write that as minus x to the power of minus 1 plus c as our answer. Here are 2 more examples that we're going to try. Again, this is a good time to pause the video if you want to try these yourself first. So with the first one, x to the power of minus 5, similar to before, this is just going to be x, so by the power rule, to the power of minus 5 plus 1, which gives us minus 4, divided by our new power, minus 4, plus c. And again, if we want to tidy that up a little, we can bring the negative sign on the denominator to the front. So we could also write this as minus a quarter x to the negative 4 plus c. Now with the last one, initially it might not look like this is in the right form to use the power rule. However, if you remember, we can write 1 over x cubed as x to the minus 3. So this integral is really the same as the integral of x to the power of minus 3 dx. And now this looks much more straightforward because it's quite similar to our previous examples. So we can say that this equals x to the power of minus 3 plus 1 minus 2 divided by the new power minus 2 plus c. Again, we can just simplify that a little and say that's the same as minus a half x to the negative 2 plus c. Now let's try fractional powers. So what would happen if we had the integral of x to the power of 3 over 2 dx? So 3 over 2 is also a real number. It's not negative 1, so we can still use the power rule. So this is going to be equal to x to the power of 3 over 2 plus 1, which is 5 over 2, divided by our new power 5 over 2, plus c. But we can simplify this a bit more, because if we divide by a fraction, this is the same as multiplying by 1 over that fraction. So this is going to be the same as 2/5 x to the power of 5 over 2 plus c. Have a play around to make sure you're happy with that step of moving the fraction up here. Here are 2 more examples. Again, you can pause the video and try them yourself or watch me solve them now. So we've got the integral of the square root of x dx. So once again, it might seem that this is not quite in the right form for us to use. However, we can write, of course, the square root of x as x to the power of a half. And suddenly this is in the right form for us to use, as a half isn't minus 1. So the answer to this will be x to the power of a half plus 1, so to 3 over 2, divided by the new power 3 over 2 plus c. And again, we can do the flippy fraction thing and say that that's the same as 2/3 x to the power of 3 over 2 plus c. With this final one here, again, this looks a bit scary, not in the right form, but we can rewrite this as the integral of x to the power of minus a third dx. So a third part comes from the fact it's the cube root of x, and the negative sign comes from the fact we've got here 1 over the cube root of x. So again, make sure you're happy with that step, but for now we'll continue. So the integral of x to the minus a third, well, as before, we do x to the power of minus a third plus 1, so to 2 over 3, divided by our new power 2 over 3 plus c. And simplifying this, do the flippy fraction thing, we get 3 over 2 x to the 2/3 plus c. Now how about we want to evaluate an integral that looks something like this? So this is a bit different to the integrals we've seen before, because instead of just having an integral that's of the form x to the power of n, we now have a coefficient in front of the x term. We have a 3 here. So we're not sure what to do with that currently, but luckily we have a new rule, multiplication by a constant rule. So this rule says that if we have the integral of a, where a is a real number, so as before, pretty much every number you'll have come across. So if we have the integral of a number times a function, then that's equal to the number times the integral of the function. So here our number a is 3, and our function is x squared. So this is saying the integral of 3 times x squared is the same as 3 times the integral of x squared. So let's see what that looks like if we finish our example. So our multiplication by constant rule says that this integral is equal to 3 times the integral of x squared dx. So we can say this is equal to 3 times, if we put a bracket and we evaluate the integral in the bracket, so the integral of x squared is going to be a third x cubed, and then we plus c at the end. And if we simplify that further, 3 times a third is 1, so that just gives us x cubed plus c. Let's try another example. So we have the integral of root 2 x to the negative 3 dx. So we can use our multiplication by constant rule to say that this is the same as root 2 times by the integral of x to the negative 3 dx. And then if we put the evaluation of our integral in a bracket next to it, so the integral of x to the negative 3, we can use our power rule, which is just going to be, so we do minus 3 plus 1, that's minus 2, and then we divide down by the negative 2, and then plus c at the end, and that equals, so we can bring the negative up to the front, and we can say that's minus root 2 over 2 x to the negative 2 plus c. Notice in the last two examples I could have put the plus c in the bracket here. The reason I didn't do that is because when we had to multiply out afterwards by the root 2 in this case, we'd have ended up with a plus root 2c. This would also be fine. Remember that the c is just telling us there's a constant term at the end, so c would be a constant term, root 2c at the end would also be a constant term. It doesn't really matter, we just need to show that we're accounting for there being a constant term that we don't know about. As a general rule, I find it easiest to add the plus c at the end of all the other terms at the stage where you get rid of the final integral sign. Notice here we're adding the plus c at the end of the line at the stage where we've got rid of our last integral sign. There was only one integral sign in this case. How about dealing with constant terms? Say, for example, we want the integral of 1 dx. So it might not look like we can use any of the rules to help us, but we can, because we can write 1 as x to the power of 0. So remember that anything to the power of 0 is 1. So if we take n to be 0 for our power rule, then this would be equal to x to the power of 0 plus 1, which is just 1, divided by 0 plus 1, again, which is 1, plus c, and this can be simplified, so x to the power of 1 is just x, dividing by 1 doesn't do anything to it, so that's just going to be x plus c. What about if we had the integral of 3 dx? Well, we can think of the 3 as being like 3 times 1. So using our multiplication by a constant rule, we can say that this is the same as 3 times the integral of 1 dx. And as we saw before, the integral of 1 is just x, so we can write that as 3x plus c. So this is the more formal way of integrating constant terms, but as you get more familiar with integration, you'll soon recognise straight away that to integrate a constant, you just add an x after it. So the integral of 1 is just x plus c, the integral of 3 is 3x plus c, equally the integral of minus 5 would be minus 5x plus c, and so you get to do these things quite quickly. How about if we had an integral like this, the integral of 2x squared plus x to the minus 4 dx. So this is a bit different to what we've seen before, because here we have two terms that are added together. So this is asking us, what is the integral of this entire term, 2x squared plus x to the minus 4? If you like, we can add brackets around that to make it clearer. So currently we don't know how to deal with integrals of this type, but luckily we have another rule. We have a sum rule that can help us with this. So the sum rule says that if we want to find the integral of the sum of two functions, say f plus g, then this is equal to the integral of the first function f plus the integral of the second function g. So in this case, if we let our f be 2x squared and our g be x to the minus 4, our sum rule says that this entire integral is equal to the integral of 2x squared, our f function, plus the integral of the g function x to the minus 4. If this was instead a minus sign in the middle, there's also a difference rule we can use, which is very similar, but just has the pluses swapped for minus signs. Using our new rule, we can say that this is equal to the integral of 2x squared dx plus the integral of x to the minus 4 dx. So again, we've taken our 2x squared to be the f function here and the x to the minus 4 to be the g function. So if we continue to evaluate this, so using our multiplication by a constant rule, this first term we can say is the same as 2 times the integral of x squared dx. And this one we can evaluate straight away using our power rule. So that's going to be, well, we add 1 to the power, that gives us -3, and we divide down by the power. So that's going to be x to the -3 over -3. So this is going to be equal to 2 times, and then if we use the power rule on this term, so I'll use a bracket here to make it clearer. 2 plus 1 is 3, so we're going to get a third x cubed here. Plus, if we simplify this term, we can bring the negative sign up. So in fact, we can rub that out and make it a minus a third x to the -3. And if you remember what I said about putting the plus c at the end of all the terms on the first line where you've got rid of all your integrals. So if you see, this line is the first line where we have no integral signs. So if we put plus c at the end here, this will be correct as your final answer. Let's try one final question. Let's try the integral of 2 over root x minus x to the power of 9. So again, you can pause the video if you want to try yourself, or just watch me work through it. So the first thing to see here is we've got a term subtracted from another term. So using our difference rule, if we let 2 over root x be the f and x to the power of 9 be the g, we can say that this is equal to the integral of 2 over root x dx minus the integral of x to the 9. And let's simplify this a bit more. So using the multiplication by a constant rule, this first term, we can bring the 2 to the front of the integral. So we can say that this is equal to 2 times the integral of 1 over root x dx. And this term, however, we can just use the power rule straight away. So we add 1 to the power, so x to the 10, but divide down by it in front. We don't need to put the plus c yet, remember, because we still have an integral sign in this line. So this is going to be equal to, well, this is in an unfamiliar form, but we can rewrite that as the integral of x to the power of minus a half. Make sure you're happy with that. Dx minus 1 over 10 x to the 10. And so we can say this is equal to, so 2 times the integral of x to the minus a half. So that's going to be x, so minus a half plus 1 is going to be a half. Divide down by a half, minus 110 x to the 10. And as this is the first line where we don't have an integral sign in, we now need to add the plus c at the end. And this is the answer, but we can tidy it up a little bit. If you remember, we can do the flippy fraction thing, so we can bring the 2 up here, so this will become 2 times 2x to the half. So that would be 4x to the half minus 1/10, sorry, I'm running out of space, x to the 10 plus c as your final answer. So you now know about the notation used for integration, how to integrate terms in x with positive powers, negative powers, and fractional powers, how to integrate constant terms, and how to integrate terms that have been added and subtracted together. So now you can integrate lots of funky integrals like these. Enjoy integrating!